So if we can perform a data fit of both dn dru theta and also this f of h, we can predict the growth of n. And if we have the growth of n, and if we have a maximum n that we think the flow is going to transition, that gives us a transition model. And the maximum n the flow is going to transition depends on the initial disturbance level. So let's take an example of some boundary layer profiles. So this is the coded up version of this transition model, okay? And basically this FTS is the normalized version of how dn dx is going to grow. So so if dre theta drex is this, then dre theta dx is let me see. So the relationship between x and rex is rex is equal to ue times x divided by nu. So that goes into here. That I think, yeah, that converts this 1 over re theta to 1 over theta, right? So this is so this is dn dre theta, which is a function of h, times 1 over theta times f of h. So what the function here does is that it's computing dn dre theta times f of h. We still need to divide the outcome of the function by theta to get the rate of growth. Okay, so that function, first of all, looks at this point. For a different h, it looks for what is the initial re theta that is going to give me any growth in the unsteady waves. So again, it's a data fit based on the different plots of this. So for every h, there is an initial point, and for this h, it has this initial point. So they are all re theta. So if you plot the initial point against the different h factors, you get a curve that can be fit using this. So this is the data fit for the initial growth, and it's an exponential function of, it's almost like exponential functions of h. So instead of fitting that re theta 0, we are fitting the log 10 of re theta 0, and the fit is turns out to have two terms. One term is a polynomial, and the other term is a 10h. Okay, so then based on the actual re theta I get, I'm going to decide if that re theta is less or greater than this critical growth re theta. If it is less than that critical, my result, the rate of growth, is equal to 0. There is no growth. Otherwise, I'm computing these two terms. One term is dn dre theta. That is this, right? This is the slope of these envelopes computed from different Falconer-Scan solutions. Okay, and that's one type of fit, and the other fit is dre theta dx. Well, actually wrote it as theta times dre dx, which is this fh, right? Because this dre theta dx is equal to 1 over theta times fh. So theta times dre theta dx is this fh. That's only a function of h. So again, that's just computed as a formula of h, include a linear term, a square term, a cubic term, and finally an exponential term. So that's this one, okay? And the result is going to be dn dre theta times dre theta dx. So that is going to give you, so if you divide the result by theta, you're going to get the rate of growth in the unsteady disturbances. Okay, so for example, this is the same function we wrote to integrate the non-interactive boundary layer equation using two equations. This is the smallest code that gives us both h and re theta, right? So in this code, we can initialize the n to be 0, right? Because in the leading edge, there is the disturbance is basically baseline, the seed disturbance. So after every integration, we are going to compute dn dx is equal to the function we called fts. It takes re theta and h. Okay, so let's say hi. We need to compute re theta is equal to uei times theta I divided by nu. So that's re theta. And dn dx is computed, and ni is going to be equal to ni minus 1. That's the previous n plus dc times dn dx. And I think I forget to multiply by theta. Right? Should I be multiplying by theta or divide by theta? I should be dividing by theta. Yeah, thanks. All right. So that is going to give us the growth. So let's plot it. So I'm going to make this 3. I'm going to plot theta, h, and my n. So running that. So this is my n. So for this boundary layer, you can see that for x goes from 0 to 6, the boundary layer supports no growth of any disturbances. Now starting from here, disturbances starts to grow, and at the end of this boundary layer, the boundary layer has grown by about e to the e squared, a factor of 10. Right? So it's a pretty mild growth, and that probably wouldn't support any transition in the boundary layer. So this is a Reynolds-Steinberg 100,000 boundary layer, and this is and under favorable pressure gradient, and that's what we get. Okay, so for example, let's make it Reynolds-Steinberg annealing, and let's make the favorable pressure gradient more restricted towards the leading edge. So I'm going to take a 10 minus c to make the curve go up faster. So it has a Blasius-like boundary layer for most of the profile. So the derivative, I think, is 10 times this, right? Let's actually close all. Okay, so now we are seeing that the start of this, the start of the growth is over here, so it's less than 1. So that's about at REX of about maybe less than 10 to the minus 6, right? So that point is about Reynolds-Steinberg based on x about maybe 500,000. Okay, and disturbances starts to grow. For example, if you have a sales plan at very quiet atmosphere, here maybe the transition location, if you look at over here, the flow is going to transition at about 5 million Reynolds-Steinberg. If you're in a wind tunnel, maybe a factor of 4 or 5 is going to trigger transition, and you're going to transition at Reynolds-Steinberg about 2 million.
I've heard n equals 9 is usually the transition point. I've heard n equals 9 is usually the transition point.
For what?
I guess I'm unsure.
So alpha, I think alpha equal to 7 or 9 is the default in X-foil. I don't remember. I don't remember, like something like 7, 8, or 9.
I think it's 9. I think we talked about it in 110.
Okay.
Last semester, a little bit.
Right. So something lower than 10, but close to 10. Right. So that's I think for airplanes with an engine, that's a very good range of transition point. Okay, so for example, if you add a bit of adverse pressure gradient, let's say 0.01 times C, the derivative, I also need to minus that, you're gonna see the transition can be a lot sooner, right? So, I mean, the range is different. It goes all the way to 40, so nothing is going to sustain that much growth. But like if you look at about, let's say, follow 7 or 8 or 9, it'll be probably here. The flow is going to transition a lot sooner than before. All right. If we follow our model that dn dx is just a function of h divided by theta, right? Which means it's inverse proportional to theta. Then what happens is that, well, this is actually these two functions. This is how fast the disturbance is going to grow. This is actually, if you take, this is the f of h. So here is Blasius boundary layer, and you can see the rate of growth is very small. It's about 0.001 to 0.002, and as you go towards separation, the rate of growth increases a lot. And it doesn't seem much, but remember, this is in exponential scale. A rate of growth of 10 times larger means you are going to transition with only 10% of the distance compared to a Blasius boundary layer. And this is the initial, this is the location where it supports initial growth. Okay, so also for high Reynolds-Steinberg, so for high H, the initial growth location is a lot earlier than for small h. And one of the reasons we see very late transition if you have favorable pressure gradient in the leading edge, as we just have in our previous code, is that the RU theta required for you to start the growth is going to be very late. Okay. All right. This is plotting the same thing here. So this is again looking at Faulkner-Scammon family of solution, polynomial velocity profile for different h, and two different critical growth factors. The ultimate location of the transition can be shifted by a huge number. So for Blasius, you can have, depending on different and critical, you have, I mean, the transition Reynolds number is in the millions, while for a larger h, the transition location is like, it can be as low as 10,000. Okay, so for high Reynolds number flows, the flow transitions on top of airfoils still in the flat region where the pressure gradient is still pretty flat. But even for low Reynolds-Steinberg, as soon as the pressure starts to increase as you go towards the trading edge, if you have a CP minus CP plot versus X, you usually have favorable pressure gradient and decreases like that. So even for lower Reynolds-Steinberg, as you go towards this region, the flow is going to transition, even for low Reynolds-Steinberg airfoils.